Thank you very much for your kind introduction, and thank you, everybody. I'd like to thank the Institute for inviting me, and I'd like to thank also Laszlo Starka for bringing me here today. There's only one important message to take home today, if it is that climate is so complicated that climate change probably doesn't have such a simple answer as we are being told. So today I'm going to be talking about a new natural climate change mechanism that may be related to how solar activity affects climate. So my goal today is to try to explain that there is an unaccounted for climate change mechanism, and this new climate change mechanism, the variable transport of heat from the tropics to the poles. And in the second place, that solar activity can change the climate by affecting this mechanism. So the first part of my talk would be about heat transport and climate change, because heat transport is a very little known part of climate. So what is heat transport? Okay, most of nearly 99.9% of the energy that enters the climate is due to the sun. And this energy enters the Earth mostly through the tropical areas. So this is in red and in blue is an actual plot of the energy balance at the top of the atmosphere. So what we have is a red area that is the part of the Earth that is receiving more energy that it is emitting as infrared radiation to the space. And there are two blue areas outside the tropics that whose size depends on the season, where there is an energy deficit because they are receiving less energy from the sun than they are emitting to space as infrared radiation. So without heat transport, the red area will heat continuously and the blue areas will cool continuously. If this does not happen, is thanks to heat transport that is represented by those purple arrows. And this is an extremely important part of climate. So the climate on any part of the Earth outside the tropics is determined by the amount of insolation, the amount of energy that comes from the sun, and by heat transport, because heat transport that not only transports heat, that energy, it also transports moisture and clouds. So if we get rain, if we get moisture, is due to heat transport because they are coupled. It is also coupled to angular momentum transport, but I will not be entering into that part today. So heat transport is a very little known part of the climate system. And this is because it's extremely complicated. Even the experts that work on heat transport recognize that there is no satisfactory theory to describe this fundamental part of the climate system. And this is because the fluid physics that are involved is very difficult to be properly represented. And there are all sizes of storms, because storms are the main way to transport heat on Earth. And there are very different sizes of storms, so it's something that is not properly understood. And if it is not properly understood, then it cannot be properly modeled. So one of the problems is that we cannot measure properly heat transport. And this is because it is taking place all the time and changing all the time through the entire atmosphere and the entire ocean. And we cannot record every part of the atmosphere and every part of the ocean continuously. So assessing, as the experts recognize, assessing meridional heat transport in the climate system is a classical question. A classical question means we don't have a good answer yet. So total transport is easy to calculate from the top of the atmosphere radiative fluxes. So satellites measure how much energy is going into from the sun and how much energy is coming out from the infrared radiation that goes into space. And the difference must be due to transport. And ocean transport is more or less calculated through surface fluxes that are due mainly to the temperature of the surface ocean. So since we more or less know quite well the surface ocean temperature, we can calculate the heat flux that is coming from there. So we can more or less calculate ocean transport, but atmospheric transport is not calculated. It is derived from total transport by subtracting ocean transport, which means that ocean transport, atmospheric transport is not independently calculated from ocean transport. And it means that this method assumes there is negligible ocean heat storage, which this is highly uncertain because heat is going continuously into the ocean in one place and coming out in another place. So we don't know how much it is stored at any given time, but we know it must be stored significant amounts of heat over the year, because the Earth is warmest when it is farthest from the sun, and it is coldest when it is closer to the sun. So this means that the heat has to be accumulated in the ocean. All of this makes that heat transport constitutes a gap in our knowledge about the climate system. It is an important gap, and since we don't know much about heat transport, we cannot model it properly. I mean, we can put into models certain values that more or less represent annual transport, but we don't know much about seasonal transport. And since heat transport is not well understood and is not properly measured, then it cannot be properly represented in the models. So this constitutes black hole in our knowledge of the climate system. And as it was famously said by Donald Rumsfeld, there are things we know, there are things we know that we don't know, but there are also things that we don't know that we don't know. And this is important because in the climate system that is so complicated, there are lots of things that we don't know that we don't know. But in general, climate scientists aren't worried about this gap in our knowledge because they consider that moving heat horizontally within the climate system, represented by this box, doesn't alter the amount of energy that is inside the climate system. So the result of subtracting heat in one place and adding it to another one is zero. So according to this principle, moving heat horizontally doesn't alter the climate system energy content. Then they also think that changes in atmospheric and oceanic transport mutually compensate, making transport almost constant. So the idea is based on this principle, was enunciated by Bjerknes, an atmospheric physicist in the 1960s, that is known as the Bjerknes compensation, is that the top of the atmosphere fluxes and oceanic heat storage remain relatively constant, then the total heat transport through the climate system will also remain constant. So if there is a change in atmospheric transport, there should be an opposite change of about the same magnitude in oceanic transport. And this Bjerknes compensation is present in all climate models. And this has been studied using 15 models, and all 15 had this Bjerknes compensation operating within the models, but the operation was different from one model to another, and it was not possible to say what physical principle was operating to give this result, this Bjerknes compensation. But obviously the models are trying to adjust transport so that they meet this compensation between top of the atmosphere fluxes. So according to the IPCC, heat transport cannot be a cause of climate change because transporting heat from one part of the climate system to another doesn't change the energy content of the climate system, and thus infrared emissions should remain the same, and there shouldn't be any climate change. But this forgets something that is very important, is that 75% of the greenhouse effect on Earth is due to water vapor and water clouds. So water in the atmosphere is actually responsible for most of the greenhouse effect. But the distribution of water in the atmosphere between the tropics and the poles is not equal. It's very uneven. So the atmospheric water content is very high in the tropics, and it's almost absent in the poles, at the poles in the winter. So what we have here is that emissions cannot be the same because the greenhouse effect is much stronger in the tropics. The water content is almost 3% there, and it's almost 0% here. So if we move heat from the tropics to the poles in the winter, we will change the emissions, and the energy content should change. So yes, heat transport should be able to change the climate. Okay, the other thing is the Bergernex compensation. The IPCC considers the heat transport is not a cause for climate change, because if we transport, if there is an increase in transport through the atmosphere, there should be a compensating decrease in transport through the ocean. So transport should remain constant. But this is not what is observed. In reality, what we observe is that we can get an increase in transport both through the atmosphere and through the ocean. So the Bergernex compensation, which is a proposition that comes from the 1960s but has never been demonstrated, should be wrong. And so how do we know that it is wrong? It is wrong because we can measure heat transport into the Arctic through the 70 degrees latitude north, and through the atmosphere there was a large increase at the beginning of the 21st century, and through the ocean there was also a large increase about nearly the same time in the late 90s. So we had an increase in heat transport to the Arctic in winter, both through the ocean and through the atmosphere. And we know this is true because what happened at that time was that there was a strong warming in winter in the Arctic. So this is a surface temperature anomaly. This graph here is surface temperature anomaly in the Arctic region, and this data is from the Danish Meteorological Institute. And we can see that Arctic warming was not a phenomenon that started with global warming. Now, most people think that Arctic warming is a result of global warming, but Arctic warming, also called Arctic amplification, actually started in the late 90s and has been going on mostly for this century. And we know this is also correct because we can measure outgoing radiation, infrared radiation, and this is NOAA data from the National Oceanic and Atmospheric Administration on infrared emissions from 70 to 90 degrees north. And we can see that there is a very large anomaly of about 8 watts per square meter that took place simultaneously to the warming of the Arctic. So now we have to think that these are winter measurements, both. So in winter, the Arctic is in the dark. There's no sun, there's no sunlight. So no heat is generated in the Arctic at that time of the year. All the heat that we are measuring here must necessarily come from the south. It cannot originate there. So what we're seeing is a lot more transport to the Arctic. There has been a change in transport. And given that the greenhouse effect is much weaker there, this is producing climate change. It's capable of changing the climate. So what is the cause of this? Okay, models and scientists say it is CO2. The increase in CO2 has caused, through a series of feedbacks, Arctic amplification. If you ask the models, they will tell you it is due to feedbacks. But this is problematic because CO2 has been increasing strongly since the 1950s. Okay, so the question is, why would it take 50 years to start Arctic warming when we know that CO2 effect on radiations is instantaneous? It takes place in nanoseconds. Then they also say it's global warming. Okay, global warming is being responsible for Arctic warming. But this is also problematic because global warming started in 1976 after a period of several decades between around 1945 and 1975 in which there was a slight cooling. So if global warming started in 1976, why did it take 25 years for the heat to reach the Arctic? This doesn't make sense also. But there is something that changed at the same time, which is solar activity. So in red, we have sunspots, monthly sunspots. And we can see that this thick curve is a Gaussian smoothing. And we can see that solar activity was very high all the way through the mid-90s, and then started to decrease in the late 90s, and it's been even lower recently. And basically, this transition happens at about the same time when Arctic warming started. So the second part of the talk will be on the relationship of solar activity and heat transport. Okay. So we know that Arctic warming is caused by the sun because it has been doing it for thousands of years. This is a very important paper, and its authors are first-line scientists, very well-known Arctic and Greenland scientists like Kobashi, Winther, and Lunier and White. These are not PhD students, they are well-recognized climate scientists. And they have analyzed changes in temperature in Greenland from ice cores, and they have come to the conclusion that they are related to solar activity. And they say that over the past 4,000 years, solar variability is associated with robust antiphase temperature anomalies in Greenland, so that when solar activity decreased, Greenland became warmer, which is exactly what is happening now. And they also say that there have been periods of warmer climate than present during those 4,000 years, which argues against Greenland warming and Arctic warming being caused by CO2 and emissions, which are very recent. So how does the sun affect the climate? Okay, there is one part of the climate that is very sensitive to solar activity, because the changes in solar activity are very small when we consider total irradiation. The change in total energy is so small, it's only 0.1%, that most scientists believe it cannot change the climate significantly because it's too small. But there is a part of the climate system that responds much more strongly to changes in solar activity. And this is the ozone layer, which is this blue band in here. Because that ozone layer, as we all know, absorbs most of ultraviolet radiation, which allows us not to go outside, you know, and due to that, the solar signal there changes a lot. Why? Because the part of the ultraviolet part of the spectrum changes a lot more than the total irradiation. So if total irradiation changes by 0.1%, the ultraviolet part of the spectrum changes by 3%, which is 30 times more. And also ozone is created by ultraviolet radiation. So when ultraviolet radiation increases by 3%, tropical ozone increases by 3% too. So we have increased energy reaching the ozone layer and increased ozone to receive it. And due to that, this is the part of the climate system that is most sensitive to changes in solar activity. So it's the part of the climate system where we should look for a solar effect. And we know the solar effect takes place because due to changes during the solar cycle, the temperature of the ozone layer changes by 1 degree centigrade. The lower stratosphere warms by 1 degree centigrade, which is about 10 times more than the changes that we can detect at the surface. So what happens with when the signal reaches the ozone layer? Okay, what we get is represented in this cartoon. The first part is the changes in solar activity through the 11-year solar cycle. And when the temperature of the lower stratosphere increases by 1 degree, what we get is a steepening of the pressure and temperature gradients. So when these gradients become steeper, zonal wind becomes stronger because it depends on this gradient for its speed. So if zonal wind is stronger, then the stratosphere becomes impenetrable to planetary waves. Planetary waves are atmospheric waves that are generated in the troposphere due to land-ocean temperature contrasts and due to mountain ranges where the wind blows through large mountain ranges. It generates a turbulence that generates planetary waves. So planetary waves are generated at the troposphere, but mainly in the northern hemisphere, where most land is located and where most mountains are located. So when the gradient becomes steeper and zonal winds become stronger, the stratosphere becomes impenetrable to planetary waves that cannot go into the stratosphere. When they can go into the stratosphere, when solar activity goes down and they reach the stratosphere, they hit the polar vortex. The polar vortex is a circle of winds, and when planetary waves carry a lot of energy. So they usually say the sun cannot change the climate because there's too little energy involved in the changes in solar activity. But planetary waves have a huge amount of energy, and they deliver that energy and momentum when they hit the polar vortex, and they slow down those winds because the momentum goes in the opposite direction. So when planetary waves hit the polar vortex, they weaken it. And this signal is transmitted from the stratosphere to the troposphere, affecting atmospheric circulation, because atmospheric circulation during the winter depends enormously on the polar vortex. The location of the jet stream and the tropical jet stream and the strength of winter circulation depends very much on the polar vortex. And this affects heat transport very much. So now we have a connection between solar activity in the stratosphere and atmospheric circulation and heat transport in the troposphere. So what are planetary waves? Well, most people have never heard of planetary waves. There are many different types of atmospheric waves. They're essentially like ocean waves, but in 3 dimensions. And planetary waves are the largest of all. They are so big that the biggest storms that can generate in the planet can fit in one of their undulations. And planetary waves are able to stop the jet stream and cause blocking conditions in winter circulation, which are responsible for the most extreme weather phenomena. So when the jet stream stops due to too high planetary wave activity, we can get tremendous floods like in 2010, or we can get very prolonged and hard heat waves like in 2003. So these planetary waves, under certain conditions, reach the stratosphere and impact the polar vortex, weakening it. And that's how solar activity affects climate. And the thing is that nothing of this is new. I haven't discovered any of this. I'm just putting things together because this was already proposed 50 years ago. In 1974, this atmospheric physicist suggested that planetary waves would be the ideal candidate for the solar effect on climate. So the question is, if this was proposed 50 years ago, why it is still not being considered and what is not being studied? Because we know that planetary waves will be the logical way for solar activity to affect climate. So this has been demonstrated through actual data, actual measurements, not models, the relationship between planetary waves and solar activity. In this article of 2011, they measure planetary wave amplitude. And planetary wave amplitude is very variable because this phenomenon of that I have shown you that the sun interferes with, which is the propagation of planetary waves into the stratosphere, depends on stratospheric conditions. And these stratospheric conditions are affected not just by the sun, they are affected by other phenomena that we know about, like the quasi-biennial oscillation, which is a stratospheric phenomenon that is very important. It's a circle of winds around the equator that changes senses every year, more or less. And it's also affected by El Niño southern oscillation, and it's also affected by volcanic eruptions. All these phenomena alter the stratosphere and they alter the propagation of planetary waves. So it's not just the sun. But the effect of the sun is very clear and can be seen very clearly because the highest amplitudes in planetary waves occur when solar activity is low. So low solar activity conditions allow more planetary waves. And this has been demonstrated. Okay, so we also know that the effect of solar activity on the polar vortex was also proposed in the 1950s. So these are things we know about a long time ago, but it seems we have forgotten and we are not studying enough. But when you look at the data here in the top graph, we see solar activity in red, measured by the number of sunspots, and in blue is the cumulative speed, anomaly speed of the zonal wind in the stratosphere at 54.4 degrees north. So what this blue line represents is whether wind speed activity is above normal or below normal. So when this curve that is cumulative goes up, it means that most of the time wind speed is above normal. And when it goes down, it means wind speed is below normal most of the time. So what we see here is that low solar activity causes wind speed to slow down. The polar vortex is weaker because there are more planetary activity. And when solar activity is high, cycles 21 and 22, in the since 1975 to mid-late 90s, the vortex was becoming stronger as zonal wind was becoming also stronger, faster. In the bottom graph, what we see is the strength of a polar vortex measured as geopotential height. And we can see that in weak solar cycles, we get this up and down, this oscillation, because it's affected by the quasi-biennial oscillation. But when solar activity is high, we tend to see that the polar vortex becomes stronger most of the time, and the oscillations become much smaller. And the polar vortex doesn't get as weak as when solar activity is low. So the relationship between solar activity and polar vortex strength is pretty much well established. Okay, so how does this correlate with climate? Well, low solar activity, we have to look for solar, the effect of solar activity on climate has to be looked in the place where it is more sensitive to it, which is the Arctic. So in times when there is low solar activity, as it has been happening since the mid-90s, what we are seeing is, as I showed you before in the graph, this is winter temperature trend, just winter, not summer. Winter temperature trend in the Arctic has been increasing enormously due to low solar activity. And this heat is coming from this ocean basin, the Atlantic, and from this other ocean basin, the Pacific, and heat is entering the Arctic through those ways. And what happens is that the warm air gets up on top of the cold air and pushes it outside, and it is coming outside through Eastern North America and Eurasia. So this is puzzling for most climate scientists, because despite global warming since the mid-1990s, what they're seeing is that winters are becoming stronger and becoming harder and colder in these areas of the planet. And climate models do not reproduce this. They say everything should become warmer in winter, and it is not happening. It is not happening to such an extreme that last winter in Mongolia, it was terribly cold, so cold that they lost 6 million domestic animals to the cold. And it was terrible for these people because they hadn't seen such a hard winter in at least 2 decades or more. So as I said, most climate scientists cannot understand this because they are disregarding the effect of solar activity on climate. Because if you say that the sun has an effect on climate, then immediately you go against the dogma, and climate scientists have a career, they don't want to go against the dogma. And so they try to explain it due to the reduction in sea ice cover. Okay, so how does this translate to climate change? Okay, the mechanism I'm proposing is that when there is high solar activity, we get a strong zonal wind in the stratosphere, as I have shown, and then this strong zonal wind causes a reduction in planetary waves reaching the stratosphere, and this results in a polar vortex that is stronger. And this strong polar vortex causes a reduction in heat transport, and since less heat is entering the Arctic, we get a colder Arctic. And since the Arctic is colder, infrared emissions to space decrease, and as a result, the planet conserves more energy. So, and this results in warming. And this is what happened between 1975 and 1997, more or less, in which solar activity was very high. So it contributed to the planet preserving more energy and warming up. When solar activity is low, okay. When solar activity is low, we get a weak zonal wind. Planetary waves activity increases, and more planetary waves reach the stratosphere. They impact the polar vortex, and we get a weaker polar vortex. And since the polar vortex is weaker, we get more heat transport into the Arctic. And this heat transport, as it's happening since the 1990s, increases the temperature in the Arctic, and a warmer Arctic results in increased infrared emissions, as I showed you. And this increase in infrared emissions results in the planet conserving less energy. Okay, so this solar theory, I have to say, it is not really a solar theory. It's a general theory of climate. And the sun is just one of the players that affects heat transport. But heat transport is actually, changes in heat transport is actually the mechanism I am proposing for climate change as a natural climate change. And I call this new hypothesis the winter gatekeeper, because the role of all these factors that affect heat transport is to regulate the amount of heat that enters the Arctic in winter. And through that mechanism, they affect the climate. So this solar mechanism has several advantages over other propositions. The first one is that it explains the energy effect disparity. So one of the problems is that the sun changes its energy output very little, yet we get a very outsized effect on the climate from the sun. And this has been one of the arguments said by the IPCC and NASA to say that solar activity does not have an important role on climate. It's because the energy is very low. But what I am proposing is that solar energy doesn't need to imply a very important energy change, because the energy is provided by planetary waves. So what we have is that the solar signal is like the finger that pushes the button of an elevator. So you push the button and the elevator comes, but you are not lifting it with your finger. It is planetary waves that are providing the energy to change the climate. So it also explains the lack of cause and effect correlation, because both the IPCC and NASA say, okay, solar activity is decreasing, yet we are seeing warming, so it cannot be the sum. Okay, it is not that simple, because the sun doesn't affect surface temperatures directly. It affects mainly Arctic energy output. And it's not the only factor acting on heat transport. We talked about ENSO, El Niño Southern Oscillation. We talked about volcanic eruptions. We talked about the quasi-biennial oscillation. So there are several factors implicated. This makes the effect nonlinear. And nonlinear means that there is no direct relationship between cause and effect. So you cannot expect a cause and effect correlation for the sun's effect on climate. Another advantage of this hypothesis is that it explains Arctic warming. Arctic warming right now is a problem for when it started, because if it was due to CO2 or to global warming, it should have started earlier. So this hypothesis explains why Arctic warming started when it did. It also explains the recent increase in Northern Hemisphere cold winters. And this is also a problem for the current theory, because models do not predict an increase in Northern Hemisphere cold winters, mainly in those two areas that I showed you, the Eastern North America and Eastern Eurasia. It also explains something I haven't talked about in this talk, that is that solar activity affects the speed of rotation of the Earth. And this was discovered in the 1960s, and there has been papers every decade. There's about 10, 12 papers discussing this effect and showing that this effect is real, that when solar activity is low, Northern Hemisphere winters, the speed of rotation is very much affected. The Earth slows down. It's only about 1 millisecond per rotation, but the effect is very clear because we measure the speed, the Earth's rotation speed with a precision of microseconds. So the effect is very clear, and it's been discussed in many articles, and nobody can explain it. Well, my hypothesis explains that since it affects global atmospheric circulation, Northern Hemisphere winter atmospheric circulation, it affects the amount of angular momentum that resides in the atmosphere, that is exchanged between the solid Earth and the atmosphere due to these changes in atmospheric circulation. It also explains why the solar effect on climate appears to have a cumulative effect, because this is one of the things that nobody really understands, because when people that study the climate of the past during the Holocene, they have seen very clearly that periods of great cooling for hundreds of years coincide with periods of low solar activity during hundreds of years. These are the grand solar minimum of the past, and they coincide so much that many paleoclimatologists are convinced that the sun has a very important effect on climate. Yet we know that the change in energy is very small. So if you get a grand solar minimum for over 150 or 200 years, you only get a reduction in 0.1% of the energy that reaches the Earth. Yet, the longer this situation takes place, the deeper the effects on climate. So large solar grand minima have more effect on climate than shorter solar minima, despite the same energy change. And this hypothesis I present resolves this problem, because when solar activity is below average, what we get is a loss of energy from the climate system, an increased loss of energy from the climate system. So the longer this increased loss of energy from the climate system stays, the more energy the planet loses, and the more it cools down, and the larger the effects on climate. It also explains why the solar effect on climate in the past seems to have a much larger effect in the northern hemisphere, because due to planetary waves originating mainly in the northern hemisphere, the northern hemisphere polar vortex is very sensitive to anything that affects planetary waves, while in the southern hemisphere it's mostly ocean. So the planetary wave activity is much lower, and the polar vortex is very strong and is not sensitive to changes. So what we get is that the northern hemisphere, due to the disposition of the continents, it has become a hotspot for climate change. So when we talk about the Little Ice Age or the medieval warm period being mostly a northern hemisphere phenomenon, this is due because they are solar induced. Finally, it also explains a part of the 20th century warming we have observed, because it coincides with a grand solar maximum that has lasted 70 years. So for 70 years of the 20th century, solar activity has been higher than normal. And according to this theory, this should cause warming, and warming has been observed. This does not say how much of the warming, of the observed warming, is due to the solar effect, and how much is due to an anthropogenic effect on climate. This is not easy to determine, but obviously, if part of the warming is due to the sun, then that part cannot be due to us, which sort of ends the climate emergency idea, because there is a natural component, so we are only, our effect on climate is less than we think. Okay, so just to finish, I would like to propose a scientific paradigm shift, which is, before the 1960s, there were lots of theories on why the climate changed. But in the 1960s, they started to make the climate models. And the way they defined climate change was to say, okay, the energy of the climate system can only change through changes at the top of the atmosphere, because that's where the energy comes in and goes out of the climate system. And to change the global climate, you have to change the energy content of the climate system. So this led to only 3 possible ways of changing climate, but they are all competing between each other. The dominant one is a decrease in outgoing energy due to an increase in the greenhouse effect due to the increase in CO2 from our emissions. Okay, so this would be the dominant theory through a decrease in outgoing energy from the Earth. Alternative hypotheses basically affect the same exchange at the top of the atmosphere over the entire planet. And this will be the people that propose that the increase in solar activity has increased the energy received by the Earth from the sun. And also the energy reflected, which is about 29% of the energy that comes from the sun, is reflected by the clouds on the surface through what is called albedo. So there are other theories competing with the CO2 theory that say that reflected energy from the Earth has been going down due to changes in cosmic rays through clouds or directly through changes in the cloud cover. So we have basically these three different looks at the same problem, which is the exchange of energy at the top of the atmosphere. But my theory has the advantage that it does not compete. Okay, my theory is that the Earth is protected from climate change by a strong greenhouse effect that is mostly dependent on water. And this here represents the amount of water in the atmosphere is from an actual graph in grams per kilogram. And what we can see is that there is this band of the Earth is basically protected from climate change due to changes in water vapor that act as a negative effect. And then most climate change or very important climate change will come from changes in heat transport because the amount of energy that can be lost at these holes in the greenhouse effect can vary quite a lot. So according to this theory, transport will be a new way of changing the climate, and it would not compete with the CO2 hypothesis. We will have to determine how much each one is contributing, but it's a different phenomenon. So I don't think the IPCC has an answer to this hypothesis. So if we go back in time, and I know there are geologists here in this talk. So what we can see is that over time, looking back 50 million years, there has been a general cooling of the planet. And this black line here is a proxy for temperature. And we can see that there has been a general cooling over the past 50 million years. And it is generally proposed that this is due to changes in CO2, but my theory offers an alternative explanation that fits the evidence better. And it is going back to plate tectonics having a very important role in climate change. So in the early Eocene, we had a very different configuration of the continents, and there was an opening in Panama, and the Tethys Sea was also open, and the Indonesian passage was very open. So we had a meridional circulation, basically. The Arctic remained closed, so there was no heat loss in the Arctic at that time. There was heat loss in Antarctica. And as the Drake Passage and the Tasmanian Passage were opening, it was becoming, Antarctica was becoming isolated from the rest of the planet. And at the same time, the Fram Strait was opening. So this was causing a general cooling until this became so open that the circumpolar current developed, and the winds of the southern annular mode, so this oceanic current coupled with wind, isolated Antarctica so much that it stopped receiving heat from the tropics, enough heat from the tropics, and it very suddenly froze, giving rise to the Oligocene. So in the Oligocene, we have quite a conundrum, a problem to explain why temperature was going up and CO2 was going down. When we look at CO2 proxies and CO2 levels, most of the CO2 was disappear at the Oligocene. So we had CO2 going to from 650 ppm to about 350 ppm, so less than we have today. And yet the planet was warming all the way to the mid-Miocene climate optimum. Why did it warm the planet? Nobody has an answer for that. According to my theory, once Antarctica became isolated by this meridional circulation, it became isolated. So the planet stopped losing heat in Antarctica. It became so cold that its emissions became irrelevant for the planet. So by reducing its emissions from Antarctica, the planet conserved more energy and became warmer all the way to the Miocene. By then, the opening of the Fram Strait was already big enough to resume cooling. And this was aided by a series of events. There was the raising of the Himalayas that have a very important effect on circulation, and they create meridional circulation. Then the Indonesian passage became more closed, and also the Bering Strait opened and the Panama Gateway closed. So basically, we altered this meridional circulation, this zonal circulation pattern into a meridional circulation one that favored transporting more heat to the Arctic and losing more heat in that part, and bringing us into the deep ice age we are now today, in which both poles are completely frozen. So it's one of the strongest ice ages of the past 540 million years. Yet we are very worried because it is warming a little bit. So another thing that this theory can explain is the effect of Milankovitch forcing. Okay, one of the problems with Milankovitch is that we know for sure that glaciations and interglacials are due to Milankovitch forcing, to changes in the orbit of the Earth, because they fit the frequency too well to be due to something else. But it is difficult to assign the relative importance of the different parameters. We have precession, we have obliquity, we have eccentricity, and it is difficult to say how the effect of these orbital changes translate into climate. So it is considered that insolation at 60 degrees north is very important for Milankovitch forcing, but this is precession. But the problem is that this has too many cycles. It's about 23,000 years cycle. Another problem is that if we look at insolation at 60 degrees south, also at the same time of the year, this will be for the month of July, okay, we see that it has the opposite effect. So if you want the planet to enter into a glaciation or to enter into an interglacial, you would like both hemispheres doing the same. You wouldn't like one hemisphere doing one thing and the other hemisphere doing the opposite thing. So obliquity is more related to the frequency of interglacial and glaciations, to the glacial cycle. And if we measure insolation instead of at 60 degrees north, at 60 degrees south, we say that it has a different variability. So sometimes there is a large difference between 60 and 30 degrees, and sometimes there is a very small difference between 60 and 30 degrees. And if we measure these differences, different in insolation, basically we're measuring the gradient, the insolation gradient between 30 and 60 degrees by subtracting them. What we see is that this difference does follow very precisely the obliquity cycle. And not only that, but if we do the same for 30 degrees south and 60 degrees south, we get essentially the same curve. So what this is telling us is that the gradient of insolation on the planet is also following the obliquity, the tilt of the axis. And this is very important because the gradient of insolation establishes the temperature gradient, and the temperature gradient is the main engine for heat transport. So these differences on temperature are the engine and should be driving different amounts of heat transport at different times. So what we have here is that when the gradient is small, we should expect less heat being transported to the Arctic, and we should expect warmer conditions because the planet conserves more energy. And when the gradient is large, we should expect more energy, more heat transport, and we should expect a colder planet. And when we superpose the temperature proxy, then we see that every time we have an interglacial is because we have a low temperature gradient in the Earth. Okay, and there is some data supporting this also from the present. Okay, so we have already seen that temperature in the Arctic in winter has been increasing since the mid-90s, late 90s. Okay, as I said earlier, heat transport is coupled to humidity transport, to water vapor transport and clouds transport. So we have already demonstrated that Arctic warming is due to increased heat transport. And we can see here the effect of increased humidity transport, which is that during the summers, Greenland snow cover has increased greatly since the mid-late 90s. And is now more snow during the summer in Greenland than there was 2-3 decades before. So this is how a glaciation should start. And I'm not saying a glaciation is starting now, we are in a warming period. This is just an effect of increased transport. But when the time is right and this interglacial starts to stop and nears its end, what we will see is an increase in heat transport to the Arctic and an increase in humidity transport to the Arctic. And we will start to see ice sheets growing instead of shrinking. So this is a nice demonstration that the increase in transport has resulted in an increase in snow, because the temperatures there are so low that even with increased heat transport, water still freezes and precipitates as snow. So basically, what I propose is that we may have been wrong about how the climate changes for the past decades, and we may have forgotten a very important thing that people were proposing in the 1940s and 1950s, that plate tectonics may play an important role in climate change, and this is due to something we know very little about, which is heat transport. And here we have some links. I have published 2 books on this, and this is my second book. My first book is available at this page here, ResearchGate.net. If you enter there, you can download it for free. It has a lot of data on it, so you can evaluate what I say. And again, I would like very much Laszlo Sarka for bringing me here today, and the Institute for receiving me and allowing me to present my hypothesis. Thank you very much.